So back in the early 2000s, Google was facing a problem on a scale that's kind of hard to even imagine. See, they were building an index of the entire internet, but they were literally drowning in the data they needed to do it. The solution they came up with wasn't just a small improvement. It was a full-blown revolution. And it all started with this really simple idea called MapReduce.
To really get a feel for the challenge, picture this. You're not just looking for a needle in a haystack. No. You're looking for one specific piece of hay in a haystack that's the size of North America. That's the kind of scale Google's engineers were dealing with every single day.
And, this wasn't just some abstract metaphor. Their main indexing system had to chew through more than 20 terabytes of raw data for every run. To put that in perspective, that's like trying to watch thousands of high-def movies all at once just to build the data structures for a web search. Their old tools were just buckling under the pressure.
So yeah, that brings us to our first big topic, Google's terabyte problem. We're talking about processing all the documents they crawled, web request logs, you name it. The sheer volume was one thing, but the complexity of actually processing it all, that was the real killer.
Before MapReduce came along, programmers were stuck writing these gigantic one-off programs for every single task. They had to figure out by hand how to split the data, how to send it to hundreds of different machines, and this is the really hard part, what to do when some of those machines, well, inevitably died. It was just a slow, incredibly complicated nightmare to manage.
So what was the big solution? It actually wasn't some bigger, more complicated system. It was a brilliantly simple idea, one inspired by old-school functional programming. This is the map and reduce abstraction, and it basically tucks away all that messy, complicated stuff behind two super simple but powerful functions.
Okay, first up, we've got the map function. Think of it as the organizer. Let's say you have a massive library and you want to count every single word. The map function is like giving each worker one shelf of books. Their only job is this: go through each book, and every time you see a word, you write that word on a sticky note and put a 1 next to it. That's it. You're just transforming the raw books into these neat little key/value pairs. The word is the key, and the number 1 is the value.
So what's next? Well, after the mappers are done, you have the reduce function, which is the summarizer. You collect that giant mountain of sticky notes from all the workers. The reduce function's job is to take all the notes for a single key, like, say, the word Google, and just add up all the ones to get the final count. It just merges all those little pieces of data into one final result.
And here's the crazy part, the part that makes this so powerful. This line of code you see here, this is basically all the logic a programmer has to write for the map part of a word count. All the really hard stuff, distributing the work, handling failures, coordinating everything, is completely taken care of by the MapReduce library itself. It's kind of like magic.
Okay, so we get the idea. Map, reduce. Simple enough. But how does this actually work across a whole cluster of thousands of machines? Let's pop the hood and see how a MapReduce job really gets done. All right, so here's the whole dance, step by step. First, the system splits your input data into smaller, manageable chunks. Then, a central master computer starts assigning map tasks to any idle worker machines. Each worker grabs its chunk of data, runs that simple map function you wrote, and writes out those intermediate key/value pairs, or sticky notes, to its own local disk. Now the master keeps track of where all that data is, and it starts assigning reduce tasks to other workers. Those workers then go and pull the data they need, sort it, run the reduce function, and write the final answer to an output file. When it's all done, the master just wakes up your program and says, "Hey, your results are ready." But the real genius of MapReduce isn't just that it runs things in parallel. It's the automatic safety net it provides. This is the secret sauce, really. This is what made it so powerful for Google's engineers, because suddenly they didn't have to be experts in distributed systems just to get their work done.
I mean, think about it. This is the critical question. In a cluster with thousands of cheap commodity PCs, failures are going to happen. It's not an if, it's a when. So, what happens when a machine just dies right in the middle of processing its data?
Well, to test this, the engineers did something that sounds kind of nuts. During a massive 1 terabyte sort job running on over 1,700 machines, they just went ahead and intentionally killed 200 of the worker machines, right in the middle of the run, just to see what would happen. And the result? It's just incredible. The master computer simply noticed that the workers had failed, reset their tasks, and then rescheduled them on other healthy machines. The job completed with barely a blip.
It was just 5% slower than a perfect run with no failures. And the best part? The programmer doesn't have to do a thing. It's all completely automatic.
But what about machines that don't actually fail, but just get, really slow? This is what they call the straggler problem. One machine might have a bad disk or some other process stealing its CPU, and it can hold up the entire job.
And the solution? Oh, it's just as elegant. When the job is almost done, the master looks at the few tasks that are still chugging along and just launches backup executions for them on other idle machines. It literally creates a race. Whichever one finishes first, the original or the backup, wins. The other one gets killed off.
Okay, but does this little trick actually make a difference? Oh yeah. For that huge sort job we talked about, just turning on this backup task mechanism made the entire operation finish a whopping 44% faster. That's a massive performance win you get for free.
All right, so we've seen the theory, we've seen the fault tolerance, but how does this thing actually perform when you throw a real-world, standardized benchmark at it? Let's check out the results of trying to sort 1 terabyte of data as fast as possible.
The numbers really do speak for themselves. The system sorted 1 whole terabyte of data, and that's 10 billion records, by the way, in just 891 seconds. That is under 15 minutes, and it did this using almost 1,800 regular, off-the-shelf machines, which just shows its incredible scale and efficiency.
So what happened when Google unleashed this new tool on its own engineers? Well, it wasn't just an update, it was a revolution. A revolution in simplicity. Just look at this timeline of its adoption. It's insane. In early 2003, there was 0 MapReduce programs in Google's main codebase. By late 2004, there were almost 900. It spread like wildfire, and for one very simple reason. It made programmers ridiculously more productive. And here's a perfect example of why. When Google rewrote their production indexing system using MapReduce, one really complicated part of it went from 3,800 lines of complex C++ code down to just 700 lines. And this didn't just make the code smaller, it made it way simpler, cleaner, and easier for any engineer to jump in and understand.
Okay, so let's just boil it all down. What made MapReduce so special? It gave programmers automatic parallelization and automatic fault tolerance, hiding all the hardest parts of distributed computing. This led to this incredible simplicity, which in turn allowed the system to scale to thousands of machines and terabytes of data. It was a total game changer.
And that really leaves you with one final thought, doesn't it? The power of MapReduce wasn't about adding more complexity. It was about creating the right abstraction to take it all away. It makes you wonder, what other massive, complicated problems out there are just waiting for their own version of a simple, elegant idea? What's the next MapReduce?